Hi everyone, my name is Qisheng Fu. I'm happy to present our paper, Deformer, Dynamic Fusion Transformer for Robust Hand Pose Estimation. This is a joint effort between Carnegie Mellon University and Salesforce Research. The problem we aim to solve is hand pose estimation, which specifically requires to predict the 3D hand mesh from the visual input like image or video. Accurately estimating hand pose in the wild is a challenging task that is affected by various factors, including object occlusion, self-occlusion, motion blur, and low camera exposure. To tackle this challenge, we propose Deformer, a dynamic fusion transformer that leverages nearby frames to generate a robust hand pose estimation in the current frame. The first pillar of our method is spatial temporal transformer, which uses self-attention mechanism to reason the feature correlation between adjacent frames. However, as the generation of key and query vectors depend on per-frame features, heavy occlusion or blurring can significantly contaminate them, resulting in inaccurate output. This observation motivates us to design the second pillar, Dynamic Fusion Module, which explicitly leverage other frames to help for a robust hand pose estimation of the current frame. The first step of the Dynamic Fusion Module is to predict 3 actual output. The forward-backward motion, which deform the current frame hand pose to the next and previous frames, plus a confidence score indicating how confident the network is about the current frame's prediction. The second step is to deform the hand poses of all frames in the sequence to the current frame, resulting in multiple hand pose estimation for the current frames. Finally, these deformed hand pose estimations are synthesized into a robust final output with the learned confidence score. Another challenge of hand pose estimation is that the fingertips located at the peripheral of the hand are more prone to occlusions and have more complex motion patterns, which makes them particularly challenging for a model to estimate accurately. As shown here, we found the error map of previous methods' predictions are unevenly distributed. We mitigate error imbalance issue by proposing the max MSE loss, which assign higher weights to hand parts with more significant errors. The max MSE loss allows the model to focus on difficult hand parts like fingertips. With the proposed deformer framework plus the max MSE loss, we achieve SOTA results on the DEX-YCB and HO3D datasets. We also partitioned the DEX-YCB test set into 3 categories based on the hand object occlusion level, which is determined by the percentage of the hand occluded by the object. The table here shows our method greatly reduces the errors in all hand object occlusion levels, especially when the hand is heavily occluded. Here are some qualitative results, which show our approach has lower and more evenly distributed errors. We visualize the confidence score predicted by the Dynamic Fusion Module. The proposed model can implicitly learn visual accountability and assign lower confidence to frames where hands are blurred or occluded. We visualize the scatter plot and the mean standard deviation of the MP-JPE on DEX-YCB test set samples with different hand object occlusion levels. Compared to the baseline, our method significantly reduces error in all occlusion levels, especially when the hand is heavily occluded. We also visualize the error versus different hand parts. Results show that the proposed max MSE loss mitigates the error imbalance issue and leads to better overall performance. That's it. Thanks for listening. Please check out our website for the paper, code, and more visualizations in video.